There is no human at the keyboard. This is OpenAI's GPT-5.5, navigating a desktop interface, opening applications, and executing tasks on its own. On Terminal Bench 2.0, a test for complex command line workflows, it scores 82.7%. Its ability to independently use tools has already led to original results. An internal version recently provided a new mathematical argument for a Ramsey number proof and formally verified it using the Lean theorem prover. But running these autonomous agents at scale requires a massive surge in raw electricity. To keep these systems online, industry leaders are aggressively lobbying for 30 gigawatts of power capacity by the year 2030. This chart compares that target to residential demand. 30 gigawatts is enough to power approximately 22 million homes. We saw the vulnerability of this scale last July in Virginia. When a single lightning arrestor failed, automated protection systems inside dozens of data centers instantly disconnected from the grid to protect their servers. In a single moment, 1.5 gigawatts of load vanished. This massive drop in demand forced power plants across 2 states to suddenly throttle their output. The grid operator barely prevented a cascading frequency spike that threatened the stability of the entire Mid-Atlantic corridor. We have built a sophisticated digital brain, but it remains tethered to a physical power foundation that was never designed to handle its intensity. To understand exactly why AI energy demand is surging today, we have to look deep inside a single server blade. This graph shows the energy required for training. While GPT-3 took about 1,300 megawatt hours, GPT-4 required over 7,000. Each generation demands a higher baseline of energy just to exist. But the newest models shift that energy drain from the training phase to test-time compute. This is the electricity consumed every time a user submits a prompt and the model begins to reason. Through chain of thought, the AI generates hidden intermediate tokens. It works through a problem step by step internally before giving an answer. Each hidden thought requires more operations. As the reasoning chain grows, the energy consumed per query increases exponentially. Deep machine intelligence requires this heavy computational burn. The current grid crisis is a direct result of how this software functions. To combat this, engineers are deploying dynamic routing algorithms to cut down on computational waste. In frameworks like R2 Reasoner, a subtask allocator shatters the user's task into individual structured thoughts. A router then sends easy subtasks to energy-efficient small language models. It only invokes the high-capacity, power-hungry models for the hardest steps of the process. This targeted allocation allows the system to maintain accuracy while reducing total inference energy consumption by 71%. They are moving toward energy sovereignty, building private, behind-the-meter power sources to avoid the instability of the aging public grid. Because thinking models require a firm 24/7 baseload, the industry is specifically targeting small modular nuclear reactors as a dedicated power source. Society now depends on these models for everything from drug discovery to critical cybersecurity networks, tasks that fail if power flickers. As we connect these autonomous systems directly to private nuclear reactors, we have to ask, are we building a new global infrastructure or just a very expensive space heater?